H₂S scavengers and corrosion control in pipelines, techniques for protecting pipelines from corrosion damage. Introduction to hydrogen sulfide, H₂S, in pipeline systems, sources and formation pathways of H₂S, corrosion mechanisms driven by H₂S in pipelines, overview of H₂S scavenger technology, triazine-based scavengers and their application, injection philosophy and field deployment, phase interaction and multi-phase behavior, mechanisms of corrosion reduction through scavenger use, performance indicators and monitoring methods, operational benefits of H₂S scavenger programs, engineering design. Considerations for scavenger selection, limitations and challenges in scavenger application, health, safety, and environmental, H₂S considerations, typical field application and equipment setup, case example, H₂S reduction in a sour pipeline, integration with broader corrosion management systems, best practices for effective scavenger use. Future trends in H₂S scavenging and corrosion control, key takeaways from H₂S scavenger application, conclusion in closing remarks. Hydrogen sulfide, H₂S, is a naturally occurring, highly toxic, and corrosive gas that is frequently encountered in oil and gas production systems. It appears in varying concentrations depending on geological conditions, reservoir composition, microbial activity, and produced water chemistry. In pipeline environments, the presence of H₂S poses significant risks not only due to its toxicity but also because of its chemical reactivity leading to severe corrosion mechanisms. When H₂S dissolves in water, it forms weak acids that aggressively attack carbon-steel surfaces, resulting in uniform corrosion, pitting, and sulfide stress cracking. This degradation can compromise pipeline integrity, leading to leaks, ruptures, safety hazards, and costly downtime. Understanding the behavior of H₂S across multiphase flow, gas, oil, and aqueous phases, is a foundational requirement for developing effective mitigation strategies. Engineers must also consider thermodynamic and kinetic factors such as temperature, pressure, water cut, and the presence of sulfate-reducing bacteria, SRB, which can elevate H₂S levels through metabolic processes. Reliable detection and continuous monitoring of H₂S concentrations are therefore essential components of a robust integrity management framework. This introduction establishes the basis for examining the importance of H₂S scavengers and their role in controlling corrosion within pipeline networks. Hydrogen sulfide in pipeline systems originates from multiple sources, each contributing uniquely to overall system corrosion. Naturally occurring H₂S is often associated with sour reservoirs, where thermochemical sulfate reduction within deep geological formations generates substantial concentrations of the compound. Additionally, H₂S may form due to microbial action, particularly from sulfate-reducing bacteria, SRB, which metabolize sulfate ions in anoxic conditions to produce hydrogen sulfide as a byproduct. This biological generation is common in produced water systems, storage tanks, and low-flow zones in pipelines. Other contributing factors include inadequate dehydration processes, which allow water to accumulate, facilitating dissolution of H₂S and accelerating corrosive reactions. Mechanical disturbances, flow regime changes, or the introduction of incompatible chemicals may also liberate trapped H₂S from sediments or emulsions. Understanding these pathways is crucial because each formation mechanism may demand a different mitigation approach. For example, systems dominated by microbial H₂S production often require biocide supplementation in addition to scavenger chemicals. Conversely, naturally sour systems may require continuous scavenger injection to manage gas phase concentrations. A comprehensive analysis of sources enables engineers to tailor strategies that optimize treatment effectiveness and enhance asset longevity. H₂S-induced corrosion is a complex electrochemical process involving interactions between dissolved H₂S, water, and steel surfaces. When H₂S dissolves in water, it forms hydrosulfuric acid, which enhances the corrosive potential of the environment. The reaction between steel, primarily iron, and dissolved H₂S results in the formation of iron sulfide, FeS, corrosion scales. While FeS layers can be partially protective, they are often unstable, uneven, or prone to spalling, exposing fresh metal surfaces to further attack. Localized corrosion such as pitting is particularly dangerous because it can lead to rapid wall penetration even if average corrosion rates seem low. Under certain conditions, especially high tensile stress and H₂S presence, sulfide stress cracking, SSC, may occur, compromising the structural integrity of the pipeline. Fluid dynamics also influence corrosion. Low flow or stagnant zones encourage water accumulation, microbial growth, and concentrated H₂S dissolution, whereas high-velocity regions may erode protective scales. Temperature and pressure variations further modify corrosion rates. These mechanisms underscore the need for effective mitigation methods, including chemical scavengers that reduce dissolved H₂S before it can participate in corrosive reactions. H₂S scavengers are chemical agents designed to react irreversibly with hydrogen sulfide, converting it into stable, non-corrosive byproducts. They play a critical role in managing H₂S within oil and gas pipelines, production facilities, and storage systems. The most widely used scavengers include triazine-based compounds, metal-based formulations, oxidizing agents, and specialty blends engineered for specific operational challenges. Triazine scavengers operate by forming thiodiazine derivatives through reaction with H₂S and are highly effective in treating gas and liquid streams with moderate H₂S concentrations. Metal-based scavengers such as iron oxide or zinc oxide react with H₂S to produce metal sulfides. Though application is typically limited to solid phase or filtration systems. Oxidizing scavengers convert H₂S into sulfur or sulfate through chemical oxidation processes but may require careful handling due to reactivity and compatibility concerns. The selection of an appropriate scavenger depends on factors including fluid composition, injection points, temperature, pressure, flow regime, and economic considerations. Scavengers are integral to broader corrosion control programs by reducing the presence of dissolved H₂S, thereby lowering corrosion potential and extending equipment life. Triazine-based scavengers are among the most widely deployed H₂S mitigation chemicals in upstream and midstream oil and gas operations. Their popularity stems from high reaction efficiency, ease of injection, and compatibility with a range of hydrocarbon systems. The reaction mechanism involves the nucleophilic attack of H₂S on triazine molecules, forming stable thiodiazine byproducts. These byproducts typically remain in the aqueous phase and are removed during water treatment processes. Effective application of triazine requires understanding phase interactions, as most triazine scavengers are water-soluble and rely on contact with water-rich regions where H₂S preferentially dissolves. Injection strategies include continuous dosing for steady-state production, batch treatments for intermittent problems, and targeted injection at high-risk points such as low-flow areas or water accumulation zones. Engineers must also consider potential drawbacks, such as formation of viscous byproducts, emulsion stabilization, or incompatibility with certain production chemicals. Proper dosage optimization ensures adequate H₂S removal without excessive chemical consumption, making triazine-based scavengers a reliable and cost-effective option for many fields. Effective injection of H₂S scavengers requires strategic placement, correct dosing, and continuous monitoring. Injection philosophy typically includes three major approaches: continuous injection, batch treatment, and targeted application. Continuous injection is preferred for systems with steady H₂S loading and stable flow conditions, ensuring constant removal of dissolved H₂S. Batch treatment is applied during shutdowns, pigging operations, or when H₂S spikes occur intermittently. Targeted injection is used in areas susceptible to water holdup, stratified flow, or microbial activity. Key engineering considerations include selecting proper injection points to ensure optimal mixing. Avoiding dead zones where chemicals may not contact dissolved H₂S, and accounting for multiphase flow characteristics. Injection skids equipped with metering pumps, corrosion-resistant piping, and monitoring instruments support accurate delivery and performance assessment. In addition, engineers often rely on coupon racks, probes, and online sensors to evaluate changes in corrosion rate and H₂S concentration. Field deployment of scavengers is an integrated effort requiring coordination between chemical vendors, integrity engineers, and operations teams to achieve consistent and reliable corrosion control. The effectiveness of H₂S scavengers depends greatly on understanding how H₂S partitions among the gas, oil, and aqueous phases during flow. H₂S is more soluble in water than in hydrocarbons, meaning that aqueous-rich zones are often primary targets for scavenger injection. However, in multi-phase pipelines, fluid stratification, slug flow, or emulsions can significantly affect reaction efficiency. Scavenger chemicals must adequately contact the phases in which H₂S is present, otherwise, treatment effectiveness declines. For example, in systems with high gas volumes, gas phase H₂S must be treated at separators or conditioning units, while aqueous phase scavenging dominates pipeline treatment scenarios. Phase behavior is further influenced by temperature, pressure, salinity, and the presence of organic acids or surfactants. Understanding these interactions allows engineers to optimize scavenger selection, dosage, and injection methodology. Failure to account for multiphase dynamics may lead to insufficient scavenging, uneven corrosion distribution, or excessive chemical consumption. A thorough understanding of fluid behavior is therefore essential for achieving reliable H₂S control. H₂S scavengers contribute to corrosion control primarily by removing dissolved H₂S from the pipeline environment before it can participate in corrosive reactions. By reducing H₂S concentration in the fluid, scavengers prevent the formation of hydrosulfuric acid and reduce the electrochemical driving force for corrosion. Additionally, some scavenger reactions create byproducts that form protective films on pipeline surfaces, although this is formulation dependent. In many systems, lowering H₂S levels also mitigates the risk of sulfide stress cracking, particularly in high-strength steels. Furthermore, reducing H₂S can suppress microbial activity, since some sulfate-reducing bacteria rely on H₂S-rich environments for optimized growth. Overall, scavenger-based corrosion mitigation is most effective when combined with complementary practices such as optimized flow assurance, water management, material selection, and periodic pigging. When properly applied, scavengers significantly extend pipeline life, improve operational reliability, and reduce maintenance costs. Performance assessment of H₂S scavenging programs requires continuous monitoring and data-driven analysis. Key performance indicators include H₂S concentration reduction in gas or liquid streams, corrosion rate measurements obtained from corrosion coupons or electrical resistance probes, and iron content analysis in produced water as a proxy for ongoing metal loss. Engineers also evaluate chemical consumption trends, pressure drop changes, and operational anomalies to verify that scavenger dosing aligns with field conditions. Sampling frequency depends on system criticality, with high-risk pipelines often requiring online monitoring using real-time H₂S analyzers. Integrity teams may integrate scavenger performance data with inspection results such as intelligent pigging, ILA, reports to validate long-term corrosion control effectiveness. Consistent documentation supports optimization by enabling adjustments to injection rates, chemical type, or treatment locations. Thorough monitoring ensures that scavenger programs remain effective despite dynamic production conditions. Implementing H₂S scavenger programs offers wide-ranging operational benefits across oil and gas infrastructure. By reducing dissolved H₂S levels, operators can significantly lower corrosion rates, thus extending pipeline service life and reducing the likelihood of failures. Improved integrity management leads to reduced unplanned downtime, lower maintenance spending, and enhanced production reliability. Safety benefits are considerable, since controlling H₂S minimizes worker exposure risks and supports compliance with occupational health regulations. Environmental protection is also enhanced, as lower corrosion rates reduce the risk of hydrocarbon spills or gas leaks. Additionally, effective scavenging enables smoother downstream processing by preventing catalyst poisoning, equipment fouling, and H₂S-related emission challenges. From an economic perspective, scavenger programs may reduce the need for costly repairs or pipeline replacements, making them a strategic investment in asset longevity and operational excellence. Selecting an appropriate H₂S scavenger requires comprehensive evaluation of system characteristics including fluid composition, temperature, pressure, flow regime, water cut, and pipeline materials. Chemical compatibility must also be assessed, as scavengers may interact with demulsifiers, corrosion inhibitors, scale inhibitors, or biocides. Engineers analyze reaction kinetics to ensure that scavenger chemistry matches residence time within the pipeline, especially in long-distance or high-velocity systems. Operational constraints such as available injection points, equipment limitations, and downstream process sensitivities must also be considered. Economic evaluation involves balancing scavenger performance against cost, logistics, and handling requirements. Some scavengers generate byproducts that may complicate water treatment or separation processes, requiring further engineering review. A structured design approach ensures optimal performance, cost-effectiveness, and long-term asset protection. Despite their effectiveness, H₂S scavengers present certain limitations and challenges. Overdosing may lead to excessive chemical consumption, formation of unwanted byproducts, or operational issues such as emulsion stabilization. Underdosing, on the other hand, results in insufficient H₂S removal and continued corrosion risk. Some scavengers may introduce solids, increase fluid viscosity, or interfere with separation processes. Chemical reactions may also be inhibited by temperature, salinity, or incompatible additives. Additionally, scavengers may not adequately address microbial H₂S generation without complementary biocide programs. Continuous reliance on scavengers without addressing root causes of H₂S formation may lead to escalating costs and diminishing returns. Engineers must therefore balance scavenger use with broader integrity management practices such as improved water handling, flow assurance, and mechanical cleaning. Understanding these limitations is essential for designing reliable and sustainable treatment programs. H₂S scavenger programs contribute significantly to improving health, safety, and environmental performance in oil and gas operations. Controlling H₂S reduces risks of worker exposure, which can lead to respiratory paralysis, eye irritation, or fatal poisoning at high concentrations. Safe handling of scavenger chemicals is equally important, as some formulations may be reactive or require specific storage and injection procedures. Environmentally, lowering H₂S emissions supports regulatory compliance and reduces the potential for atmospheric sulfur deposition. Proper disposal or treatment of scavenger byproducts must also be considered to prevent contamination of water bodies or soil. Training personnel in safe chemical handling, establishing spill response plans, and monitoring workplace air quality further reinforce HSE compliance. By integrating scavenger programs with broader safety frameworks, operators can maintain a safe working environment while protecting surrounding ecosystems. Field application of H₂S scavengers typically involves dedicated injection skids equipped with metering pumps, corrosion-resistant piping, check valves, and monitoring instrumentation. These systems are designed to deliver precise chemical dosages to selected injection points within the pipeline or production facility. Sampling ports allow operators to monitor H₂S levels upstream and downstream of injection to verify treatment effectiveness. In multi-phase pipeline systems, injection is often located at liquid-rich regions to maximize contact between scavenger and dissolved H₂S. Additional equipment such as static mixers may be installed to improve dispersion. Field personnel routinely inspect pumps, calibrate injection rates, and collect fluid samples for laboratory analysis. Integration with telemetry systems enables remote monitoring of chemical usage and injection performance. This operational setup ensures reliable and consistent scavenger application, supporting long-term corrosion mitigation strategies. In a typical field scenario involving a sour pipeline with elevated H₂S concentrations, implementation of an optimized scavenger program can significantly reduce corrosion risk. For example, a pipeline experiencing intermittent H₂S spikes may adopt a continuous triazine injection strategy supported by real-time monitoring tools. Field data before chemical introduction may show high dissolved H₂S levels, elevated iron counts in produced water, and accelerated corrosion rates based on coupon analysis. Following injection system installation and dosage calibration, operators observe marked reductions in H₂S concentration, stable corrosion rates, and diminished operational disruptions. Periodic adjustments to injection rates ensure alignment with fluctuating production conditions. While each field presents unique challenges, such case studies consistently demonstrate the effectiveness of scavenger programs when properly engineered and monitored. H₂S scavengers form only one part of a comprehensive corrosion management program. Effective long-term pipeline integrity requires integrating scavenger treatments with mechanical cleaning activities such as pigging, which removes deposits that may trap H₂S or harbor bacteria. Corrosion inhibitors may be added to form protective films on metal surfaces, complementing scavenger action. Regular inspections, including intelligent pigging, ILI, ultrasonic testing, and visual assessments, provide insight into corrosion progression and help validate scavenger performance. Water management strategies such as dehydration, separation optimization, and microbial control further reduce the conditions that promote H₂S formation. By coordinating chemical, mechanical, and inspection-based strategies, operators establish a holistic approach that enhances asset reliability and extends equipment life while optimizing chemical use. Achieving consistent performance from H₂S scavengers requires adherence to engineering best practices. These include performing laboratory testing to evaluate chemical compatibility and reaction efficiency before field deployment, optimizing dosage based on real-time H₂S data, and validating mixing and dispersion through flow modeling or field observation. Regular monitoring of corrosion indicators, chemical consumption rates, and operational behavior helps identify deviations and enables timely adjustments. Collaboration with chemical vendors ensures access to technical expertise and updated formulations. Training field personnel on proper handling, injection procedures, and sampling techniques enhances reliability. Documenting performance trends and treatment history further supports continuous optimization. By following these best practices, operators can ensure efficient chemical use, improved corrosion control, and enhanced operational safety. Future advancements in H₂S scavenging and corrosion control are driven by technological innovation, environmental considerations, and the need for increased operational efficiency. Emerging scavenger formulations focus on higher reaction efficiency, reduced byproduct formation, and improved environmental compatibility. Digital monitoring technologies, including advanced sensors and real-time data analytics, enable more precise dosing and predictive corrosion modeling. Integration with automated chemical injection systems allows responsive treatment adjustments to dynamic production conditions. Research into hybrid chemistries combining scavenger and corrosion inhibitor functionalities shows potential for enhanced performance. Additionally, increased emphasis on sustainability encourages the development of biodegradable and low-toxicity formulations. As the industry continues to evolve, these advancements support safer, more efficient, and environmentally responsible H₂S management. H₂S scavengers play a crucial role in mitigating corrosion and improving operational safety in oil and gas pipelines. By chemically removing dissolved H₂S, scavengers disrupt corrosive mechanisms and reduce risks of equipment failure. Their effectiveness depends on correct selection, strategic injection, and continuous monitoring. Although challenges exist, including cost, byproduct formation, and chemical compatibility, proper engineering and field execution minimize these limitations. Integrating scavenger programs into broader corrosion management frameworks maximizes asset protection and operational reliability. Ultimately, effective H₂S control enhances safety, environmental protection, and economic performance across pipeline systems. The management of hydrogen sulfide in pipeline systems is essential for ensuring safe, efficient, and sustainable oil and gas operations. H₂S scavengers offer a practical and effective means of reducing dissolved H₂S concentrations, thereby mitigating corrosion and improving overall system integrity. Through proper selection, optimized injection strategies, and comprehensive monitoring, scavenger programs deliver substantial operational, safety, and environmental benefits. Their integration with mechanical cleaning, inspection, and broader corrosion control methods ensures a robust and long-term approach to asset management. As technological advancements continue to enhance chemical performance and monitoring capabilities, future scavenging strategies will become increasingly efficient and environmentally responsible. Closing this presentation, it is evident that H₂S scavengers remain an indispensable tool in modern pipeline corrosion management.